Please, Lucas, go ahead.
Okay, so hello everyone, and thank you for the opportunity to speak today and present mine and Karol Życzkowski's current work in progress, actually. So this is not yet finished and not yet published, and I'm just putting this out there to maybe get, and my goal is to get some maybe ideas on potential applications and maybe some insights from the community. And as was introduced, the title of the presentation is Matrix, Logistic Equation, Fractal Level Densities. So we'll go back to the basics of chaotic models and to the logistic equation. Just a short recap to begin with. So we all know what is the logistic equation, I believe. So it's just a very simple map that iterates some initial point according to a quadratic equation, which has a single parameter denoted A here. And we have a well-known bifurcation diagram for this map presented in this picture here for the parameters between 2.5 and 4. And if the parameter is 4, we have a fully chaotic behavior, and the distribution of the final point follows the arc sign distribution, which will be shown later. And here I also marked some interesting points that will be used throughout this presentation. So for the parameter A equal 10/3, we have just these two cycles. And we have two chaotic windows 3.8 and 3.9, which will also appear on some of the results. So what was our motivation? Well, our motivation for this work is to try to find some potential applications of the logistic map in quantum information processing, quantum science, and to try to somehow connect all these results with the theory of random matrices, because that's what we focus on in our everyday research. And as it turns out, there have been some attempts on generalizing the logistic map to matrix dynamics. For instance, this work looked into the case of n equal 2, so for two-dimensional matrices, and we thought what we can try to do a bit better and try to extend this. And coming from the quantum information background, we of course like Hermitian matrices. So we started with the Hermitian case, and we thought what we can do with an arbitrary size matrix n and still have some scalar coefficient that characterizes the dynamics denoted A here. And so we thought what will happen if we have such matrix just such equation that just iterates some initial matrix, which is well defined. That means that it's between 0 and the identity matrix. So of course we don't get any runaway dynamics. And because this is all Hermitian, we can diagonalize this easily. And turns out this equation is also hermiticity preserving in this case. So we can translate this entire dynamics into the dynamics for just the eigenvalues of the initial matrix. And just look at the diagonal. What we get is that the behavior follows the behavior for a standard logistic map. And yes, so for large dimensions, we have something that we can call a fractal level density of the Hermitian matrix, which can look like this. Here's an example. We start with some random Gaussian unitary matrix of size, it was 1000 here. We normalize it so that it fulfills this condition here. And then we iterate through our equation for A equal 3.8. And the red curve shows the initial distribution of eigenvalues, which is just a semicircular distribution. Then after only 3 iterations, we see we have some very nice chaotic behavior, and after 30 iterations, we reach what we can call a steady state, and we achieve a fractal level density for the final matrix. And of course, for all the intermediate matrices for other values of t. So this can be formulated as a following proposition, that we have a Hermitian random matrix, and with a continuous support, meaning that the eigenvalues are contained in the unit interval, and we iterate this matrix by the matrix logistic map, and then the level density is given by the invariant measure UA that is equivalent to the invariant measure for the ordinary logistic map. But of course, we can try to go a lot further than just Hermitian case, and we can start thinking about non-Hermitian matrices, and this case becomes much richer in behavior and much more complicated. So, because for non-Hermitian matrices we can have, of course, general complex eigenvalues, so that's not a good point to start. So we look at the singular values of an arbitrary matrix X here, which has some fixed dimension n, and this is just the notation. The sigma 0 is the diagonal matrix containing the singular values on the diagonal. U and V are unitary matrices, and here's the definition of just to recall the definition of the singular values as the square roots of eigenvalues of XX dagger. And we also assume that, again, the singular values are not greater than 1, so that we also don't get a runaway behavior. And we have defined a somewhat modified map in this form that leads us to the dynamics of the vector of the singular values, which again looks like just the vector or iterated through the ordinary logistic map. And for this case, we have a fractal density of the singular values, not the eigenvalues. And this is illustrated here for the parameter a equal 3.9. And again, for some initial distribution, we have a quarter cycle distribution now. And after just 3 iterations, again, we obtain some nice fractal level densities, which converge to the blue steady state after just 30 iterations. And this can be summarized similarly to the case of Hermitian matrices, but just for the singular values, not the eigenvalues, meaning that the singular values in this case are given by the invariant measure that corresponds to an appropriate logistic map. But this is not the full picture for the case of the non-Hermitian matrices, because we can try to ask some other questions. We can look at the radial density of the modulus of the eigenvalues of this matrix. And this is where things get a bit more interesting and exciting, because if we have some random, again, matrix sampled from the Ginevra ensemble and normalized appropriately, and Ginevra ensemble, just to recall, is an ensemble of random matrices that have independent, identically distributed normal entries. And they are appropriately normalized so that we don't get a runaway behavior. And now we have, imagine we have some matrix X0 and we iterated t times through our equation, and we observe the behavior of the modules of the eigenvalues. And what happens then? So the initial distribution here shown in the pink color, that is well studied, and the eigenvalues of the Genibru matrices cover uniformly a unit disk on the complex plane. So if we look just at the radial density, the density of the modules of the eigenvalues, then we get this nice linear behavior. And this artifact here, this drop-off, is due to finite size effects. This is in the field of random matrices well known and well-studied phenomenon that for finite values of the dimension, even if it's relatively high, like say a couple of thousands, this behavior still exists. Then after just one iteration, we get this light blue distribution of the modules of the eigenvalues, and after 30 iterations, we obtained the dark blue behavior. What is interesting here, that for the parameter A equal 3.4, for the traditional logistic equation, we should get a 2 cycle, and so we would expect that we will obtain something like maybe 2 peaks here or 2 Dirac deltas at this distribution, but we obtain something that is continuous. And at first glance, this might be surprising, but from the point of view of random matrix theory, there exists what is called a single ring theorem that states that this radial distribution can be only that the eigenvalues of such matrices can only form a single ring in the complex plane. So the eigenvalues have to the radial density of the eigenvalues has to have this continuous property then. And here are some references where this phenomenon is introduced. They are maybe not that important from the perspective of the dynamics, but from the perspective of random matrix theory, this was quite a surprising result when it was discovered. So what happens now as an example? Let's look at the fully chaotic behavior, at least for the singular values. So if we have, again, some random matrix and we start iterating it through our logistic equation for the fully chaotic behavior, so the parameter A is equal to 4, then the singular values, as mentioned in the beginning, will follow the arc-sine law. And let's recall the distributions here. But what will happen to the radial part of the eigenvalues? So this is quite not trivial to obtain. And the resulting distribution is shown here. The black bars is just some numerical histogram, and the red line is the analytical results of the resulting distribution. I don't present the resulting distribution because although it has a closed form, I don't think it would fit nicely into one slide due to complicated way we get it, which I will just mention in a minute. And the green line here denotes the theoretical asymptotical maximum value of the modules of the eigenvalue, and as mentioned before, this drop off here is due to finite size effects, and this is obtained from 1,000 simulations of matrices of order 500. And how do we obtain this red curve? This is obtained via something that is called the Hagerup-Larsen theorem. which allows us to connect this distribution of the singular values and going through lots of Cauchy transformations and reverse Cauchy transformations, and to obtain in the end this red curve. But as I said, it gets very complicated, and the closed form is very tedious to write, because we have to go through Cauchy and inverse Cauchy transformations, which produce these square roots of higher order polynomials, and it's just hard to manage and to present in the slide. And of course, we can think about going even a step further, because for now we had the matrices as the inputs of our logistic map, but our parameter was still a scalar, and we can also try to change that. And this will result in some coupling between the logistic equations that correspond somehow to each of the eigenvalues, which will be explained in a bit. And just to recall that coupling to logistic equations have of course been studied since the 80s, maybe even sooner. And the easiest and the simplest coupled logistic equation system is just one in which you take a convex combination of two logistic maps. And we can study some interesting phenomena like synchronization of attractors when the onset of chaos occurs, etc., etc. But our model is a bit different than that. Because let's say we have some matrix of size n, and the matrix coefficient now that is Hermitian and has all the eigenvalues positive. And let us limit ourselves to only iterating Hermitian matrices through our equation. So our equation is given in such a form, where A here is a matrix parameter, and we have equation of this form, and A is actually just this B dagger. And of course, it has to fulfill this nice property that is less than 4 times the identity. Otherwise, again, we get a runaway behavior of the equation, and we have a potential problem. And if we assume for a minute that the initial condition to this equation, some H0, is diagonal, then we can think of the diagonal entries of A represent just some ordinary parameters for a logistic equation of each map, where the number of maps is equal to the number of the dimension of the matrix n, and the off-diagonal elements describe coupling between these maps. And again, here are some simple examples of the behavior. So we start with a very simple one. So first, let's start with a behavior when we have A equal to a diagonal matrix which has half of the values set to 4 and the other half set to some value A when A is 10 over 3. And this yields a mixture of two densities, the arcsine, which comes from this part of the values, and two deltas, which come from the A equal 10 over 3. And this is shown in this picture here. The red line is, of course, the arcsine the distribution. And of course, we are not limited to such simple diagonal matrices. We can try to perturb this just a bit. So consider some block diagonal matrix A, which has this form. So we have an identity matrix times such a simple non-diagonal matrix with epsilon here on the off diagonal, and beta is just a constant that ensures that we don't get a runaway equation, that everything stays between 0 and 1. And So we have this being this nice block diagonal form, and this is what we obtain as the steady state distribution of the eigenvalues. We see some remnants of the behavior for this uncoupled case. Especially these two peaks here are the same that are for the case here, but we see they are somewhat smoothed, and we have all these other parts of the distribution that lie between 0 and this peak, this left peak, and between the right peak and 1. And the red curve here is just a conjecture because we're not able to prove it. And this is the arc sign distribution, but not between these two points, which correspond to the 10/3 cycles of the logistic map. And of course, having such a rich possible choice of parameters, because we have a matrix here, we can play around with this, and we can think about very simple models, like a two-dimensional model coupled by such matrix A, where the matrix B is just something with some AB parameters on the diagonal and some epsilon here of the diagonal. And sorry, this should be the capital delta. I don't know. Must have missed the backslash when I was writing it. Sorry for that. And we see that this leads to some quite strange dynamics. Which limits as the space of possible values of the parameters A and B as epsilon grows, and the plots here actually are the sketches of the Lyapunov exponent for this system as the largest Lyapunov exponent for the system as a function of the parameters A and B. Okay, and we can look also somewhat closer on this Lyapunov exponent. So here we present the dependence of the Lyapunov exponent on off diagonal for the dependence on the dependence of the Lyapunov exponent on the coupling parameter epsilon, and just as a function of the parameter A. So we take this, we look at this diagonal line here basically. So we set A equal to B and look at this diagonal line here. And for various values of the epsilon. So for epsilon equal to 0, we of course recover something that is the well-known Lyapunov exponent behavior for the ordinary logistic map, but changing this value of epsilon puts us into somewhat new regime. And we see that we have in some cases, when you look here, we have onsets of chaos when the initial logistic equation, the ordinary logistic equation, was not chaotic. So, to conclude now, we have introduced nonlinear matrix dynamics via the matrix logistic map, and this was done for two separate cases. The logistic map for Hermitian matrices, which led us to fractal level densities. And then we had the logistic map for non-Hermitian matrices, which required some modification of the logistic map to obtain something that works like a logistic equation for the singular values, leading to fractal distribution of the singular values, but leads to smooth radial distribution of the complex eigenvalues, and this is related to a phenomenon in random matrix theory known as the single ring theorem. And a possible extension of this nonlinear matrix dynamics is a logistic map with a matrix parameter, and this leads to non-trivially coupled logistic maps. And we hope it will offer us a playground to study some questions concerning synchronization in such systems, structure of attractors, and a detailed study of the onset of chaos. And thank you.
Thanks, Lucas, for your very interesting presentation. Very elegant. Do we have any questions for Lucas? Let me ask, was it possible to observe more than one attractor in your matrix system?
Oh, this is a very interesting question, actually. So the short answer is no. We weren't able to find such a good such cases to have a good observation, and this is related to some numerical convergence problems we get when trying to work with these matrices. And why is that? Because of such behaviors like this. When you have these transitions here that in theory should have a hard limit, but they do not have. It's sometimes very easy to get a runaway equation, and this becomes unstable numerically, and it's hard to study. I don't know if that answer satisfies you, but...
Yeah, thanks, Lucas. In your numerical experiments, is there any scaling between the order of the matrices and the number of iterations that you have to wait until reaching the stationary distribution?
We didn't do a systematic search for this, but because we didn't feel that there is a need, because we looked for matrices we studied matrices of size 2 and of size 1000, and usually after like a few dozen iterations where some near the steady state distribution, we didn't see much change. So I don't think that it's a problem in the model we present.
Thanks, Lucas.